along with the next one. This one, we're going to talk about the correlation coefficient R, and for us to understand exactly what it tells us. And then we're going to go on to see an interpretation, and then we're going to work some of the application problems from the homework. So we're probably only going to need 4, maybe 5 videos here, and we'll be finished up with this here over the next couple of days. So we're going to introduce methods for determining whether a correlation or association between two variables exists and whether the correlation is linear. That's really the only correlation we're going to work on for this class. For linear correlations, we can identify an equation that best fits the data, and we can use this equation to predict the value of one variable given the value of the other variable. And this is the regression equation of the regression line. It's going to ask that you remember a lot of your stuff from Algebra 1 of y equals mx plus b, and how we can plug numbers in to use that to make predictions, and when those predictions are appropriate and when they're not appropriate. When we can use the regression equation and when we can't. And we can also present some methods for analyzing differences between predicted values and actual values. Don't worry about that so much. So we're going to introduce linear correlations. We're going to identify independent, explanatory, and dependent response variables. And again, think about y equals mx plus b. X was always your independent variable and y was always your dependent variable. And when we get into the prediction section, as we get into regression, we'll see what this looks like. We're going to recognize types of correlation graphically and symbolically, positive correlation, negative correlation, and no correlation. This particular video, we're going to talk about how to interpret the correlation coefficient R. We're going to work on finding them later. How to test a population correlation coefficient rho using the Pearson R table. This is the one section where we will use the Pearson R tables, and those of you that have already done some of the homework problems have already been doing this. This is a form of a hypothesis test, but it's a little different, and we're going to find out in the second video that the hypothesis and alternative hypothesis is always the same. The null hypothesis is always there is no linear correlation, or rho equals 0. And the alternative hypothesis is always there is some linear correlation. It could be strong, it could be weak, but there's some there. So we're going to learn how to find the equation of the regression line, and StatCrunch does that for us, and how to predict y values using the regression equation. So those of you that have worked with this before, you were plugging x in to the regression equation and solving. StatCrunch has a really neat feature where you can plug in your x value, and when you hit compute, it will give you the y value and do that calculation for you. We want to know when the regression equation is not appropriate for making predictions, and we want to make predictions when there is no linear correlation. So we're using paired sample data, sometimes called bivariate data. We find the value of R, usually using technology. We'll be using StatCrunch. Then we will use that value to conclude that there is or is not a linear correlation between two variables. We can often see a relationship between two variables by constructing a scatter plot. So if we notice here, this one starts high and goes low. That tells me it's a negative linear correlation. If x and y both increase, positive linear correlation. Where everything's just kind of scattered about, no correlation. And this is a nonlinear correlation. This is actually a quadratic correlation, but we will not be, that's beyond the scope of this class. We're only going to concern ourselves with negative linear correlations, positive linear correlations, or no correlation. So this video introduces the linear correlation coefficient R, which is a numerical measure of the strength of the relationship between two variables representing quantitative data. This is about numeric numbers. The symbols that we commonly use, and in this case it's different. It means the number of pairs of sample data. We have ordered pairs. For every x, there's a y. So this is the pairs of data. R, linear correlation coefficient for a sample of paired data, and then rho, linear correlation coefficient for a population of paired data. The requirements: the sample paired data must be a simple random sample of quantitative data. Visual examination of the scatter plot must confirm that the points approximate, they don't have to be exactly, they approximate a straight line pattern. The outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. So the linear correlation coefficient R measures the strength of the linear relationship between paired quantitative X and Y values in a sample. We're going to use the homework problem from, I've got it labeled as chapter 1 here. I may be changing that. It might be it might be the second homework problem. I'll have to check that after I get the video posted. But the question is, which value of R indicates a stronger correlation? They give us 0.711, or R equals negative 0.937. It tells us to explain our reasoning. So I did a very bad job with paint, and I approximated the location. And we have my negative 0.937 here, which I left at 0. That was a really bad drawing. And then over here we have a 0.711. This graph is something that's useful when you're doing application problems. We're not going to be able to decide whether there's correlation or not because we don't have the critical values. We don't have enough information. But this is, right now I just wanted to show that this is out here really close to -1. This is on the other side. It's a little farther away from 1. So the approximate location of each point is located on the above diagram. The diagram shows the R value of negative 0.937 is farther from 0 than 0.711. Recall the idea of absolute value.